Sam's, what are you doing? You look like you got some problems.
Oh, that burrito I ate this morning was not sitting well.
Oh, burritos, that causes gas sometimes.
Yeah.
You must be having some gas problems.
I'm thinking so.
Huh. You know what we're going to talk about today?
It was so good, though. Oh.
Yeah, well, it might have been
It's
good.
like the size of my head. Had chicken and beef and beans and rice, green chili on top.
You know, Mr. Sams, we're going to be talking about Boyle's and Charles and Gay-Lussac's laws. You know,
Oh.
Boyle's law has to do with like pressure and the volume. So you're probably feeling some pressure inside of your gut. Yeah, and so that's caused by gas.
Increasing the volume of my gut as well.
Yeah. Yeah, so why don't we talk about that today?
Okay.
All right, so let's go ahead and do that. So, guys, we're going to talk about gas laws today. So today, Mr. Sams, we're going to learn about Boyle's, Charles, and the Gay-Lussac's law.
Good. I feel better now.
Do you?
Yes.
Wonderful. You must have relieved some of the pressure.
Perhaps.
Yeah, okay. So our goal is to find about the relationship between pressure and volume of a gas.
All right.
And when you try to find that, that's something called Boyle's law.
Okay.
So if you increase the pressure, so let's say we have a fixed quantity of gas, and I increase the pressure.
Okay, pressure goes up.
What's going to happen?
I'm pretty sure the volume's going to go down.
Pressure's up, volume down?
Yeah.
So I drew it wrong.
Yes, you did.
Oh, okay.
Yeah, I always think of it like a piston. If you shrink it down, you decrease the volume, and the pressure gets more inside that container.
All right, so here's what he's saying, guys. If I have a piston right here, okay, and I have a plunger right here.
Think of like a bike pump.
Like a bike pump. Yeah, bikes. I like bikes.
Sure.
Okay, and then if I do this in that plunger and I push it down harder, because I apply more force,
right.
The same gas down here and the same gas down here, this, of course, will have less volume, higher pressure.
Correct.
Okay, this is called Boyle's law. Okay, now, you know, Mr. Stams, this summer I had a kind of interesting experience. I rode my bike up a mountain.
As you do often.
As I do often,
yes.
I know. But while I was doing that, I conducted an experiment.
Oh.
So I think we should watch the Mr. Bergman Bike Up the Mountain video.
Okay.
And see how this applies to what we've been learning.
Okay.
Okay. Go. Here I am at the base of Mount Evans. Now, if you look back up here, you're going to see a bunch of mountains, and I'm about to climb that mountain here. But I have myself a bag of Pringles Minis, and I want you to notice the bag's kind of roughly like this, or you can push it down. It feels a little full, probably, compared to what you're probably used to if you live at sea level. But think of the gas particles striking this all of a sudden. But we're about to climb on our bicycles the highest paved road in America, which is the Mount Evans Road, and we're going to see what this bag looks like, and it's actually an application of Boyle's law. So we'll see you there in a few minutes, or hours. Rolling. And we're on the highest paved road in North America. Pikes Peak Highway, riding up. Mr. Creekshauser, what altitude do you think we're at?
We're right around 12,000 feet.
12,000 feet. So, now look at my Pringles potato chip bag. Now, compared to what we saw, it's totally full. Boyle's law in action. How's that Boyle's law? Well, you see the gas inside, the pressure is the same. I'm breathing hard. The pressure is the same, but the external pressure at this high altitude is lower, and therefore the molecules, here I'll try and show this. Here, let's pause here. The molecules that are hitting this, well, there's fewer of them because we're at a higher altitude. But the molecules on the inside, the air molecules on the inside, they're the same number. Therefore, the bag expands. Now, we're going up there to the top of Mount Evans, 14,200 feet, I think. When we get there, I anticipate that this bag will be either fuller or possibly it will explode in my backpack and I'll have a mess. Let's see it. I'm at the top of Mount Evans. It's a windy day, and I got my bag of Pringles Minis. Look at how big that is. Totally full. I think it looks, because of the Boyle's law, not very much air up here, even though it's windy, so it caused the potato chip bag to expand. You know what I ought to do? I should eat some.
Okay, you looked really tired. You actually had to get off your bike to talk to us there for a while.
Well, you know, there's a problem. There's not as much oxygen up there either.
And that's because there's lower pressure up there.
That's right.
And the lower pressure at the top of the mountain made the bag of chips get a greater volume. So
That's
pressure
correct.
was down, volume was up.
Exactly.
Okay.
Exactly. So that is Boyle's law. This is actually, folks, what you do to copy this down. This is the graph of Boyle's law. So pressure up, and the volume goes down. This is the graph.
Right? This is said to be inversely related. And the way we know that is if you plot a graph of volume versus 1 over the pressure,
you get a
straight line. And that is the equation. Now, actually, the equation is this. The meaning of the graphs, pressure is inversely proportional to volume, which we said already. All right. If one variable doubles, the other one is half. So a lot of people want to say up and down. That's true, but the key thing, students, to understand is that if you double one variable, the other one will cut in half. Now, Mr. Sams, what would happen if I were to triple the pressure?
The other one would go down by a third.
Yeah. So it's like it's the inverse, the reciprocal, guys.
Or not by a third, to a third.
To a third,
its original
actually,
one was. Yeah,
that's correct. Now, there's actually a chemical, or not a chemical equation, but an equation is P1 V1 equals P2 V2.
Okay, so P is probably pressure.
Yeah.
V is probably volume.
Yeah.
What do those little 1s and 2s mean?
Well, the first one is the initial condition. So when I was at the bottom of the mountain, I could have measured the pressure and the volume.
Okay.
And then at the top of the mountain, the pressure would be different,
Okay.
and therefore the volume would be different. So it's
Okay.
just like the initial conditions. 1 would be at the bottom of the mountain, and 2 would be at the top of the
So
mountain.
initial and final, you're implying that a change has taken place to that gas.
That's exactly right.
Okay.
Okay. So let's actually do an example. So a 2-liter balloon is taken from Woodland Park, pressure of 0.75 atmospheres, to the top of Pikes Peak. Well, this is Pikes Peak, but I went up top of Mount Evans.
Okay,
The same
pretty
idea,
close.
really. What's going to happen to the balloon? Not a bag of Pringles, but a balloon. Actually, let's. So here we have the balloon in Woodland Park, and here's the balloon at the top of Pikes Peak, right? So let's actually do it on a blank screen here.
Okay.
Okay, so let's do that. All right, now what I want to do. So here's our problem, Mr. Sams. I got our calculator out. In fact, everybody, you should get your calculator out.
And
Okay.
yours probably doesn't have feet, but ours does.
Yeah, we've got the cool calculator of the feet. All right, so what I want you to do is you're going to write P1 and then V1. So let's determine what these are.
Okay.
So we have a 2-liter balloon. So
Okay,
what is that?
2 liter is a volume.
All right.
And that's its initial volume
So
that
that's
we're given.
2 liters.
Down at Woodland Park.
All
Okay.
right. In Woodland Park, pressure is 0.75 atmospheres,
Okay.
which is about right where we live.
Yep, pretty close.
So I'm just
Depends on
writing
the day.
down what I know. And then there's going to be a P2 and a V2.
Okay, so what else do we have? We go to the top of Pikes Peak, so a change has occurred.
Yeah.
We're at a different place with a different pressure.
So the pressure's 0.54.
Pressure's 0.54 atmospheres. So we have a different pressure. Now, pressure went down. So I'm going to guess that the volume is going to go up.
Yeah, so this is what we're trying to find, and we should predict it goes up. So we're going to use the equation P1 V1 equals P2 V2. Now
Okay.
P1 is, we're just going to plug in our numbers.
Plug and chug. 0.75
0.75
atmospheres.
atmospheres times
2 liters.
2 liters is equal to 0.54 atmospheres times
V2.
V2.
And we're going to solve for V2.
Well, this is easy, Mr. Sanders. This is like easy algebra.
It is.
You just divide both sides by the number next to the V2, right?
Yep.
0.52.
5.4, actually.
Oh, 4?
Yep.
Whatever it is. Okay. So now I've got my trusty calculator, so it's going to be 0.75 times 2 divided by 0.54. And you said it's going to go what?
It should go up.
Up. And guess what you get? 2 points. So V2 is 2.77 or 78 probably with sig figs. 78 liters. So
Okay.
it went from 2 to
2.8.
8-ish.
Yeah, so it went up. So that makes sense. The
Yeah.
answer makes logical sense.
Well, and we
I'm
saw that
assuming
with the
that.
Pringles potato chip
Right,
bag. It
exactly.
went up, didn't it, as
Yeah.
we saw it. All right, so that's called Boyle's Law.
Okay.
Now, there's another law that also we're going to talk about. It's called Charlie's Law. Or Chuck's Law, what do you call it? Chucky. So what is Chucky's Law? Sounds like Chucky. Isn't he like some
He's this little doll in horror films from
horror
the late
guy,
80s,
right?
early
Yeah,
90s.
I'm not into
yeah.
that thing. But okay. Yeah, so volume versus temperature. So that's so we're not talking about pressure anymore, just volume and temperature.
You spelled verses wrong, by the way.
Did I?
Yep.
Well, that's
Good thing
not-
you're a science teacher.
Yeah, I know. So really, so as temperature goes up, what's going to happen to the volume?
Temperature goes up. I don't know. Why don't we figure this out?
Actually, I'll tell you, the volume goes up.
Oh, you're
But
just gonna tell
I will
me?
show you a
Okay.
cool example. This summer, actually, so if you have low temperature, here's the balloon, and if you increase the temperature, it'll get larger.
Okay.
A cool application to that is hot air balloons. Well, this summer, Mr. Sams, I was at a triathlon. I like to do those things.
Yes.
And at the triathlon,
Crazy.
at the festival, they actually had hot air balloons.
Oh, that's fun.
And so I kind of showed a video of hot air. That's why we have the hot air balloons in our background
Oh,
picture
yes.
here. And so, yeah, so let's watch the video of me. At the triathlon. Here we have an amazing example of gas laws, Charles's law. What I've got is in front of me is a bunch of hot air balloons. In fact, one's way already up in the sky right here. And if you'll notice, occasionally what they're doing is they're throwing some fire. You can see the fire right there.
that they're throwing in. They're heating up some air, and as they heat up the air, what they're doing is they're causing the gas to expand, the air to expand. It is less dense when it is hot than when it is cold. Charles' law says is the higher the temperature, the higher the volume. It's a direct relationship, and by doing that, that of course allows these hot air balloons to rise up in the sky, as we can see with the one right here, who's way, way up there already. He's the first one to take off, and now the rest of these are about to take off in just a moment. Occasionally you will see the fire turn on in here, and that fire is an indication, of course, they're trying to keep the balloon going higher and higher by expanding that gas using Charles's law. So these guys who love to fly their hot air balloons are utilizing Charles's law over and over and over again.
Okay.
Okay. Okay, so you can see that as the temperature goes up, the volume expands, which actually reduces the density and causes the balloon to float in the sky.
Pretty cool.
That is pretty cool, isn't it?
I bet you're going to show me a graph now.
Yeah.
Hey, look, a graph.
It's kind of weird orange, isn't it?
Yeah.
Oh well. Hey, as the volume goes up, the temperature goes up. By the way, an important thing, guys, is the temperature must be in Kelvin.
Always, for any gas law, temperature has to be in Kelvin. Do not try to do these in Celsius. It does not
How about Fahrenheit?
work. No, we never use Fahrenheit.
I
What
don't know,
are
I
you
just
talking
thought I'd
about?
say
No,
that. It's fun.
no. Always has to be in Kelvin.
Guys, Kelvin it is. Now, how do you get from Celsius to Kelvin?
Add 273.
Remember, it's Celsius plus 273
Yeah.
is the Kelvin temperature.
Yeah, the problem with Celsius is it can go in the negative land, and these equations don't work if you
Yeah,
have to go down to
don't
negative
work
land.
negative.
Yeah.
So, what's the meaning of the graph? Volume is directly proportional to the Kelvin temperature.
So if the Kelvin temperature is doubled, the volume is doubled.
Yeah. If it tripled,
it would be
it's
tripled. Hey, look at that.
Yeah.
Actually doubled.
and the
I didn't
equation
even know that was there.
is V1 over T1 equals V2 over T2.
Okay.
You know, we should probably do an example.
example.
So let's do an example problem.
Hey, look, it's the balloon.
Here's the issue we're going to have. We've got a balloon. You remember that show? What's the name? It was Wilson. Was the
The little volleyball, Tom Hanks.
Tom Hanks in that movie.
Castaway.
Yeah, we've got an
thank
audience,
you.
guys. So yeah, Castaway. We can get it from the peanut gallery. Castaway, and he had Wilson. Well,
Yeah.
if we took Wilson,
Hey,
we put him in an oven.
My students remind me to tell you a story about that movie in class.
Okay, there you go. All right, so put Wilson in the oven. He's going to get bigger.
Okay.
Yeah. So okay, well let's do the problem here.
Okay.
So let's do that. Everybody, what do you need to get out? Your
Calculator.
There you go. All right, a balloon has a volume of 5.43 liters. Actually, you know what I like to do, Mr. Sams?
What's that?
Is not advance the slide when I want to. Is I want to draw pictures. I think
pictures are good. Yeah.
So I have a balloon. Okay, here's a balloon. And what do I know about this balloon?
It has a volume of 5.3.
5.43 liters.
0.43. I can't talk. I've had way too much coffee.
And
today.
25 degrees Celsius.
I don't like Celsius.
We're going to say, what's the volume going to be when it jumps to 95
Celsius.
degrees Celsius?
But we don't do Celsius.
I know. So, but let's write down what we know. So
Okay.
we know our volume, our V1, is 5.43 liters.
Okay.
Okay, we're good.
T1.
Our T1 is 25 degrees Celsius, but that's wrong.
Yeah, we don't like that.
So I have to add
273.
273. Now I'm not even using my calculator for that because that's
No.
too easy. That's 298 Kelvin. I'm just adding that in my help.
You're
My
amazing.
help.
Amazing.
And my T2 is 95 degrees Celsius. Is that good?
No, we need Kelvin.
You add 273. Now I can't do that in my actually.
368.
368 Kelvin. You guys could add that up. Now, actually, let me also say here, this is the volume in liters. The thing that's interesting about the volume is you can put it in any unit you like,
That's convenient.
as long as you have the same units. Now we have all our numbers. We're just going to plug it into our equation. Remember, the equation was V1 over T1 equals V2 over T2. V1 is 5.43 liters. T1 is 273. I've got to put that in Kelvin. Is equal to V2, that's my X, if you will, divided by 368 Kelvin. Now, how do you solve that problem?
I would just cross multiply.
Yeah,
That's all for
remember,
me.
folks, you can cross multiply, and when you cross multiply, you can get the answer. So I can take 5.43, so I'm over my calculator, 5.4, I messed up there. Delete. All right, clear. I'll do this again. 5.43 times 368. And actually what I could do, guys, is I can actually divide right by 273. So I'll just do that.
If you don't
Divided
believe us,
by-
ask your math teacher.
Yeah, I might explain it in the call-outs, too.
Yeah.
And I get a V of 3 liters.
Now, the temperature went up, so our volume should go up, and if we compare 5.43 to 7.3, obviously the volume went up, so it makes sense, so you probably did your math right.
Yeah, that wasn't too hard. Okay.
All right.
So we should probably, we have one more to talk about, so let's move on to that.
Okay.
And that's called the Gay-Lussac law.
Okay.
All right, two guys, Gay and Lussac, who figured this out.
Yep.
Pressure versus temperature.
All right.
Okay. When the pressure goes up, so now we're going to keep the volume the same. Think bicycle tire. Bicycle tire is about the same size.
Okay.
If you increase the pressure, what happens to the temperature?
It goes up.
Yeah, that's exactly right. Temperature goes up.
Another thing, if any of you have ever played paintball or have anything with a CO2 cartridge, as that CO2 cartridge, as you use it, the pressure in the cartridge goes down,
and it gets cold.
And you'll notice that the cartridge gets cold and the temperature goes down.
Yeah.
So it's two things going on.
So pressure, we would say, is directly proportional to the Kelvin temperature. So it has a graph, and it's the same like the last one, but it's pressure versus, if you double the pressure,
You double the temperature.
double the temperature.
The
Not
Kelvin
only the Kelvin temperature.
temperature.
And so here's our equation, P1 over T1 equals P2 over T2. Well, I think we should probably do an example. Actually, here we'll use a bicycle.
Hey, look, a
tire.
bike.
Get a bike, and so what happens as you travel, start on a cold day, and then the tire warms up?
The tire warms up, the pressure should go up.
So let's see what that's the question. So here we have a cold day, and it got hot, you see, and there's a hot pavement. That's the picture. Okay, so a bicycle initially has a pressure of 120 pounds per square inch, etc. So notice, okay, let's do the problem.
Okay. Now the pressure is 120 psi. Now, last problem you said the volume could be in any unit.
Yeah.
Does the pressure, can it be in any unit as well?
Yeah, so this is in pressure of pounds per square inch, which is
So
how
I don't
bicycles
have
are
to
made.
convert that to anything, right?
No, you could. You could convert it to atmospheres or whatever, but you don't need
You
to.
don't need to. But the temperatures I have to put in Kelvin.
That's good.
All right, so let's write down what we know.
P1 is
120 psi.
psi. That's a pressure unit.
Okay.
And temperature initially was 25 degrees Celsius.
Okay.
And so my T2 is 35. Got hot. That's a hot day.
Okay.
35. So I'm just trying to find P2, right?
All right, so let's get those temperatures in Kelvin.
So, okay, so if I add 273, actually, we've just seen that's 298.
298,
right?
yeah.
Well, and that's easy because this is only 10 degrees above that.
Oh.
So this would be 308, right?
Yep.
So I'm going to plug those into my numbers or into my equation.
P1 over T1.
So it's P1 over T1 equals P2 over T2. So I'm going to say 120 psi divided by 298 Kelvin is equal to P2 over 308 Kelvin.
I'm going to say cross multiply again.
So you can say 120 times 308, I'll wash this through, is equal to 298 times P2. Divide both sides by 298. 298 cancels, and 298, and that will give me my answer. So here's my calculator, 120 times 308 divided by 298 gives my answer.
124 psi. Now the temperature went up, so the pressure should go up, and we can see it went from 120 to 124.
That's,
so
that's not a big change,
No.
is it? But the temperature only went up from 298 to 308.
Right. It's not like we doubled the temperature or anything like
Right.
that.
Yeah. Okay.
You know what? I'm getting kind of hungry.
Are you?
Yeah, I could go for a burrito.
Oh, not with me around.
Carne
you aren't.
asada.
See, he released that gas earlier, and oh my gosh, the pressure went down and filled the room.
I love burritos.
One thing about gas is they filled the space they're in.
Yeah, we'll
We
talk
can
about
fill
that
this room.
soon.
Yeah. Okay.
Graham's law of effusion and diffusion.
All right. We'll see you later, guys.